I'm very excited today to introduce my first speaker, Stefan Saasen. He's been on the Bitbucket team for many years now, done many things, knows the tool, the Bitbucket server inside out, worked many years on it, and now he's an architect and has been working. His last project has been, developing search for Bitbucket Cloud. But I wanted to say, he's the guy that decided I would be an Atlassian. He's the guy who hired me 4 years ago, foolishly did so. And but I'm eternally grateful for him for giving me a chance. And please, let's just give him a round of applause. Stefan Saasen, everyone.
Thank you very much. Thanks and welcome. Good morning. I hope you have enjoyed AtlasCamp so far. Last year, we released code search for Bitbucket Server. And just on Tuesday this week, we made the public beta for search in Bitbucket Cloud available. So if you are a member of an active team in Bitbucket Cloud, you might already have access to search in Bitbucket. Otherwise, you can request it. If you think about search, you might think that search is largely a solved problem. Information retrieval has been a major research concern going back many years, even decades. And there are great commercial and open source search engine implementations available in the market. So adding search to Bitbucket, that should be simple, right? Well, let's look at some of the requirements that the team faced when we started to build search in Bitbucket Cloud. Bitbucket hosts more than 17 million repositories for our users. Those 17 million repositories amount to approximately 600 terabytes of raw compressed repository data. And that's just our primary data store. I sat down and did a bit of a back-of-the-envelope calculation and thought, well, how many files would we have to index if we indexed everything in Bitbucket? And on the conservative side, I estimated that that would be around 13,000 million, that's 13 billion, see what I did here, files that we would have to index. So that's quite a lot. But in addition to the sheer amount of data, we also face a significant rate of change. There are more than 87,000 index events per hour at peak time. So those are all events that signify some change to repository content. So our challenges when building search for Bitbucket Cloud are twofold. One, we need to build a data-intensive application at scale. And secondly, we also want to have a general-purpose search engine. You should be able to search for any text file in a repository. But we want to focus on code search as a particular use case. So in order to motivate some of the decisions that we made, I'd like to talk a little bit about how a search engine works under the covers. It's a bit of a search 101. If you think about searching for text, you might be thinking of using a tool like grep, which is essentially doing a linear scan over files on your machine, which is surprisingly efficient on today's hardware. But you can imagine, looking at those numbers, that that is not an approach that would scale. So search engines tend to have a two-step approach where you do some pre-processing called indexing. You insert data into a specialized data store, and you use that data store to service search requests. And this is a very high-level view of how a search engine works. And I'll briefly step through some of the components. It all starts with you having to acquire some content that you can index. Part of that decision is also you have to decide how you map that content to what is called a document. Documents are a central concept in search engines, and they're just a collection of fields. So for us, that is fairly simple. A single file in a repository is a single file document in our search engine. Other than that, it's simply extracting text. You might have text files, you have to do some encoding detection, or you might have to transform binary files. But at the end of the day, that step ends with you providing a stream of characters. You then feed that stream of characters into the next phase, and that is broadly called the analysis phase. And the first step is that you want to turn that stream of characters into a stream of tokens. think words. That includes detecting word boundaries and also includes removing punctuation characters, for example. That stream of tokens will then have to be transformed into a stream of normalized tokens. And there are a number of techniques that will be applied. For example, you might do case folding. You might want to do case folding. You might have to deal with accents or diacritics in a uniform way. Or you might want to deal with grammatical variations. Algorithms like stemming or lemmatization try to identify the root form of a word so that regardless of whether users enter a singular or plural form of a word, it still can be found. Again, there is a lot more to this topic, but it's important to point out that the decisions that you make composing that analysis chain has a huge impact on the quality of your search results for that given use case. I'll show you a quick example pointing out some of the challenges, especially in relation to code. Here's some example text that looks like it's a source code file. You can see there's some assignment and what looks to be a method call on an object. Applying that analysis chain leads to this following stream of normalized tokens. So you can see we have lowercased all the terms. We removed some punctuation characters, but we retained that joining dot. Remember the method call? We kept that token as a combined token, but we also inserted new tokens that represent both the method and the object. You might have also noticed that we removed that single character. Ultimately, this is all a trade-off between retaining characters to improve search precision on the one hand, and on the other hand, not unnecessarily bloating the index size, because that also impacts search performance. And the next step, all those terms or tokens get inserted into what is called an inverted index or an inverted index file. It's a bit of a tautology, but that's the terminology that is being used in information retrieval literature. And conceptually, that is very simple. That is simply a often sorted set of terms in what is called a dictionary that are mapped to document lists of document IDs. Those are also called posting lists. There's a lot more to that in terms of the actual data structures used, what's kept in memory, what's kept on disk, et cetera, et cetera. But an important part of this is also capturing some statistics. So here I called out the document frequency as one of those statistics that is being captured. And that is simply how many documents contain that given term. With the data captured in this data store, we can now start servicing search requests. So imagine this is a query that a user entered. The central idea with this approach is to apply the same or a very similar analysis process to the query. So in our case, this is what the user entered, and this is the normalized query. That means that we can deal with some variations of users typing in or entering search requests. And then it's simply a lookup in our inverted index. We look up that normalized term, and that posting list, that is essentially your result set. That is the list of documents that contain that term. With just that information in place, we can already service or express Boolean expressions. So here is a Boolean AND. We apply the analysis process again, and then Boolean expressions are simple set operations. So you look up both terms, and a Boolean AND is an intersection of those two posting lists. So those are all the documents that contain val and foo.bar. If you followed closely, you might have noticed that I only talked about the result set. But there's an expectation that the best matching document is the one that is in the top of the the top of the result list. And that is what ranked retrieval is all about. This single slide on ranked retrieval doesn't really do all the theory behind that approach justice, but the general idea behind ranked retrieval is to look at document and term statistics in the inverted index to calculate a score for each document in the result set in relation to the query that the user entered. For example, there are algorithms where documents that have more occurrences of a given term receive a higher score, and rare terms have a higher contribution to the overall score. That works well for natural language and our general purpose search engine, but it's not necessarily the best fit for code search, because code is not the same as natural language. And a brief example kind of highlights that. So here I searched for repository service. And repository service is an interface that is defined in that repository. But the top result is some other class that happens to use repository service. So it's contained in the import list, and it is mentioned a few times in the rest of the document. So according to the traditional ranked retrieval approaches, that should be considered more relevant, but it mentions that term more often. But I was looking for that interface, and it's not in the result list. It's probably on page 2 somewhere. So to improve that use case, we added something to Bitbucket Cloud code search that we call language-aware syntax extraction. It's a bit of semantic search, if you will. So what we do is, for every file that we index, we parse that file if that file is in a set of supported languages and extract declarations. That means things like class names, type names, methods, symbols, etc. We then add those declarations to the document that represents that file, and at query time, we boost those documents that contain that term in their declaration list, which leads to the following result. So now my top result is that repository service interface that I was looking for, even though it only mentions that term once. So this is a great improvement on search quality for the code search use case. We're certainly not the first ones to parse source code. It has been done for many years in different fields. Think compilers, text editors, IDEs. But we have to do that for billions of files. Which brings me to the next challenge that we faced, and that is that we had to build search at scale. It sounds great, like who wouldn't want search at scale? But what does it even mean? Scalability is defined as the ability to cope with an increase in load. That could be temporary load spikes, but it could also be the ability to cope with increased load due to growth. The initial numbers that I showed you, that's the current statistics. I looked them up 2 weeks ago. They're probably already out of date. So the search system needs to be able to handle that future growth of Bitbucket as well. If you think about scalability as a requirement for your system, it's crucial that you identify what is actually driving the load on the system. In search, we distinguish the indexing pipeline, which happens asynchronously in the background, and the query pipeline, which is on the user request path. For indexing, we identified the rate of change as the load parameter driving load on the system, which leads us to an attached optimization goal of improving or maximizing the indexing throughput. The requirements for the query pipeline are a little bit different. Here, the load parameter is the queries per second that we can support, and we have an attached performance goal of minimizing the query response time. So if you type something in, we want to give you a result as quickly as possible. If you think about the qualities, architectural qualities that your system should have, scalability being one of them, with the motivation of having to support Bitbucket at scale, but it's also important to think about other qualities your system should have. Those are also sometimes known as the ILIDs, so scalability, testability, maintainability, flexibility, etc. And for Bitbucket Search, we kind of focus and optimize on the following 4. And to be honest, personally, I'd argue that's kind of the most important ones for any application. Scalability, I already mentioned that. Functionality, well, if your search engine doesn't return search results, it's not particularly useful even if it was infinitely scalable. And security is a bit of a given as well. But the other quality that we optimized for, or that we had in mind, is reliability. And reliability is defined as the probability of successfully executing an operation or returning a response. And this can be measured by looking at successful requests versus errors or unsuccessful requests. But at the end of the day, it simply means that your system needs to work correctly even when things go wrong. So with this kind of set of goals in mind, let's now look at how search is actually implemented in Bitbucket. So this is the very high-level system architecture of Bitbucket Cloud Code Search. And you can see it is a composition of services that run on top of Amazon Web Services. And we're using Elasticsearch as our actual search engine implementation. And the fact that we're running on top of a cloud platform also reinforces this desire to build a reliable system, because cloud platforms tend to optimize for flexibility and elasticity, but not necessarily for single machine reliability. And an important technique when you think about reliability is to introduce some redundancy. So when I say service here in this context, I mean a set of instances that run behind a load balancer. And in Amazon, you tend to put them in different availability zones, think data centers, which means whenever a single instance goes down, there are still more copies of that service running that can deal with incoming requests or the load. Let's now look at some of the different components, and let's start with the indexing pipeline. So its goal is to essentially get all the changes from Bitbucket into Elasticsearch at the end of the day. So we are interested in all changes to repositories. That includes users pushing changes or merging pull requests or doing online edits. And for those events, we use Bitbucket Connect webhooks. If you haven't heard about webhooks or Bitbucket Connect hooks, webhooks in particular, I highly recommend a talk of a colleague of mine, James, who will be talking this afternoon about using Bitbucket Connect webhooks. So I highly recommend to go to his talk if you are interested in that topic. If you haven't heard about webhooks before, there's simply HTTP requests that the host application sends to your add-on with some predefined payload that matches whatever event, the event that happened. For us, thinking about that rate of change that I mentioned, like we get constantly events coming in, HTTP requests coming in. So we also wanted to aim for the webhook ingester service to be highly available. And one technique that we applied here is that we have an internal buffer that is backed by an SQS queue. So incoming webhook requests, we don't do any form of processing, we just put them onto that queue, and then offload any form of processing to happen off that queue in the same service. Though things like the verification of JOT tokens, validation of messages. But that means that we've minimized the opportunity for a service going down whilst it is in the process of responding to webhook requests. That happens off queue, and if the service was to go down, another service could pick that message up again. We then transform the webhook request into a very minimal index event message that we put onto another SQS queue that is shared between the services. That service is also responsible for responding to Connect add-on lifecycle events. If you install a Connect add-on into Bitbucket, it will send you an installation handshake, again, just an HTTP request with some payload that contains, amongst other things, a shared secret, which you can use to verify that the incoming requests haven't been tampered with, and you can also use that to make outgoing API calls to Bitbucket from your add-on. Managing and storing those secrets, if you make any API calls, is another common Connect concern, for which we have a dedicated service. But if you have another add-on, that could all be in the same application. It's a different dedicated service in our case, because we need access to those shared secrets from both the indexing and the query pipeline, which unfortunately also means that that service is on the critical path. So again, high availability, an important design goal. And looking at what that secret store does, you need to add and remove a secret, and you need other services, support other services just looking up a secret. That maps very nicely to a key value store. So we built that secret store on top of a DynamoDB table. And DynamoDB has the nice benefit of being highly available if you're only using eventually consistent reads. So if your service needs to be highly available, you also need to consider what your data store supports or what kind of guarantees it gives you. Something unrelated to the topic of reliability or high availability is the fact that we store secrets encrypted. And if you are handling secrets in your add-on, I highly recommend you do that as well. Everything that's in Dynamo, even if that data were to go missing, no one could actually do anything with it because all the secrets are stored encrypted. So again, highly recommend you do that as well. The next service, and arguably the most important one in that whole pipeline, is the indexer service. And it is the service that is responsible for synchronizing repository data in Bitbucket with index data in Elasticsearch. I briefly described the overall data flow. Imagine a user pushes changes to a repository, webhook request flows through the pipeline, the indexer subscribes to that SQS queue, gets the index event message. We then look up the secret. We use that secret to authenticate against the Bitbucket API and look up the latest commit on the default branch. For code search, we only index data on the default branch. We then compare that against the latest commit that we successfully indexed. And if there are any differences, we retrieve those differences from the Bitbucket API as a set of contents changes. And we do that in a streaming fashion. At that point, the indexer is responsible for transforming those file changes into documents that we bulk insert into Elasticsearch. An important point here is the fact that we have the ability to follow an asynchronous messaging pattern by using a queue, which is quite useful because it decouples failures, say, in the indexer from failures in the webhook ingester. Compare that to, say, synchronous communication using REST calls. In a synchronous communication, if your recipient is down, you're also impacted. Here we can use the queue as a temporary buffer, for example, if the indexer is down or if there are any load spikes. So we can run the indexer at a pretty constant ideal throughput rate and use that queue to kind of ride out load spikes. And as I said, it's also a nice fault tolerance pattern. So look for opportunities where instead of using synchronous HTTP calls, you can use a message queue. Part of the transformation, and I mentioned that initially, is also doing syntax extraction, and for that we use a dedicated service. It's a dedicated service because we want to be able to scale this service out individually. Its API is extremely simple. Think of it as being a function from file content to a list of qualified declarations. Whilst the API is simple, the service unfortunately is not. We have to put in a lot of engineering effort to make sure that this service does not become a bottleneck for our indexing pipeline. And again, think about indexing throughput is an important goal for us. So we're using a mix of scaling out, just adding more instances as load demands, and scaling up, trying to find the ideal instance size with CPU and memory for that given task. Also tuning number of processing threads, etc. Again, focusing a little bit more on reliability of the system, you also want to avoid any single point of failures. And if I think about our whole system, Elasticsearch is our data store, and we thought that could be a single point of failure. To be fair, Elasticsearch itself, we're using Elasticsearch clusters, already tries to improve its fault tolerance by replicating data. So index data is not just kept on a single node, it is replicated to other nodes, which means if an Elasticsearch node goes down, the overall cluster still keeps working. But stepping back, from our point of view, we still considered Elasticsearch, that cluster, to be a single point of failure. So we added another layer that we call the routing proxy, or the routing aware load balancer. So what we do is search in Bitbucket Cloud is scoped to an account. You can search across all repositories and all projects within an account, but that gives us the ability to partition the index data using the account key. So what we do is we assign a particular account to an index on a cluster and forward and route all the requests to Elasticsearch through this routing load balancer to the correct index on the correct cluster. That means if there was any incident affecting the entire cluster, we would have limited the blast radius of that incident, only affecting a subset of the Bitbucket customers, but not all customers. And it also gives us the opportunity to make performance improvements. If we end up co-locating very active accounts, say to the same index, we can move accounts to a different index or even an entirely different cluster. And it also allows us to very easily scale out our Elasticsearch infrastructure by simply adding more clusters. I mentioned the query pipeline, and I have to admit it's not much of a pipeline. It's really just a single service that provides the REST API that is being used by our search UI. But that search UI sends the query to that query service, and we also do some query parsing. We have our own custom search DSL, and the reason for that is twofold. Firstly, we want to have tight control over what types of queries are possible. Elasticsearch itself supports a wide range of queries, but some of them are extremely expensive. Think of wildcard queries or regex queries. So we want to have tight control over what types of queries we send to Elasticsearch so that we don't overload the system by accidentally or maybe maliciously creating lots of very expensive queries. But secondly, we also wanted to provide a custom search DSL that works well for the code search use case. So we support everything that you'd expect from a search engine, like phrase queries, nested Boolean expressions, but we also have added a set of modifiers that allow you to filter down search results based on, say, file extensions or programming language. If we think about that flow, a user does a search, a request comes in, we then go and look up the secret for the given account. We ask the Bitbucket API for the permission graph of the current user, which is essentially all the repositories the user has access to within that given account. We then use that to create a query that we send to Elasticsearch. So you can see that there are multiple services and multiple network calls involved servicing a single search request. Usually we try to look for opportunities to parallelize those requests, which unfortunately we cannot do because we have to sequentially step through those services, one after the other, which means each of the services needs to have very tight service level agreements, very tight latency, so that we can reach our overall goal of minimum query response time. So by now, I hope you have a bit of a kind of intuition or high-level understanding of what happens when you go to Bitbucket and do a search. I also want to share, I guess, some of the things that we learned while building search. With search, we embraced a service-oriented architecture, or I hate to say it, but it's very popular, a microservices architecture out of necessity. Our scaling requirements didn't really leave us much of a choice. It's very popular, but it's also very costly, and I'll touch a little bit on that. And one of the things that's quite costly is that fact that we ended up building a distributed system. And you might be familiar with this very famous quote from Leslie Lamport, who states that a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And a slightly less tongue-in-cheek definition of a distributed system, it's essentially a system with a shared nothing architecture, so only machines communicating over the network, but that network can exhibit non-deterministic partial failures. So simply by moving from a single machine to a distributed set of services, you onboard a whole range of new problems. So let's look at some of the things that we used, not only to address, I guess, the challenges of building a distributed system, but by addressing the challenges of building large-scale search. Firstly, and I mentioned it initially, it's quite important to really define your non-functional requirements. I mentioned that when I talked about scalability, but it's really hard if you optimize for the wrong goal to retrofit your system if you find out that you're actually scaling or optimized for the wrong scalability goal. It's also quite useful and important to try and identify some general truth or principles. Sounds a bit hand-wavy, nothing much to disagree with, so let me give you a few examples. One of the principles that we identified and kind of put down is that we only wanted to store derived data in Elasticsearch. Our primary data stores in Bitbucket are the database and our storage system for repository data. We didn't want to add another one, which also has a nice side effect is that even if all our clusters were to go down and we lost all the data, all the backups were gone, we could simply recreate all of that data from primary data sources. Another principle is that we wanted to apply bounds everywhere. That includes things like bounds on memory, data structures in memory. So we try to run the indexing pipeline in constant memory, for example. More importantly, though, if you think about communicating over network, it also requires to put very tight timeouts on network calls so that you don't sit there and wait indefinitely until something comes or doesn't come back. And it's useful to state that as a more general principle because it's really hard to identify all the different cases where you might want to apply bounds, so putting that down as a general development principle is quite useful. Maybe not quite a principle, probably more like an attitude is the fact that if you're wanting to build a reliable system, you have to build for and assume failure everywhere. As I mentioned, simply by communicating over unreliable networks, you onboarded a whole new range of failure modes that you have to account for. So put that down as a kind of general principle. If you're aware of the type of system that you're building, it's also useful to identify common and well-known patterns that apply to that type of system. So for example, we're following a 12-factor style for building stateless services. 12 factors are, well, unsurprisingly, 12 factors that describe how you build stateless services, including, for example, runtime configuration or how you log, ideally as structured logs. That allows you to operate those services in a uniform way, even though these services might be implemented differently. I was a little bit reluctant to put the next point down, eventual consistency. You could have a whole talk on that topic alone. I put it down as a reminder that simply by moving to a distributed system, a lot of assumptions that are true on a single machine are just simply not true anymore in that new world. So be very reluctant to try and apply existing patterns that work well and assume, for example, strongly consistent data. Don't apply that blindly to the system that you're building. In our specific case, we try to see if we can deal with and live with eventual consistency, which also applies to our own system. So a user making a change, that change is not immediately visible in search results. So we allow for some lag. There are a lot more patterns, and I, again, highly recommend a talk from a colleague of mine, Diego. He will be talking tomorrow about 5 techniques and patterns for building fault-tolerant systems. So again, it's a very, very important topic, and there's a whole presentation on that. The last one that I just put down here is really not one of the broad patterns. It's really a fairly simple techniques we found useful, and it is using feature flags for rolling out changes. So you decouple making the feature available from actual code deployments. The last one is one I generally find useful for any form of software development. Be very careful where you spend your innovation dollars. You have a limited amount of capacity for trying out new things, new technologies, new libraries, and especially with a large-scale system, you spend a lot of time operating that system. So if it's simple and you really understand not only the semantics of the language, but the runtime characteristics, you're in a much better place. Lastly, maybe the most important advice or learning from our point of view was that for a system like this, tooling is key, is absolutely essential. There are many, many machines running at the same time, machines coming and going because we scale out and scale in again. So logging into machines to tail logs, that's just not a scalable process. So you want aggregated logs. You want to be able to look at logs from many machines, even across service boundaries. Related to that, you also want to have monitoring and metrics that you can aggregate. There can show you dashboards that allow you to visualize trends or detect anomalies. I showed you the query service, which means that a single user search request ends up doing many network calls. Distributed tracing is quite useful. It allows you to trace a single request across system boundaries and also visualizes and shows you where you spend your time. So if a user comes and says, hey, my query is slow, that allows you to identify what service or what request might have added to that additional latency that you're seeing. The last one that I wanted to point out is maybe less of a tool, it's more, again, a pattern is applying artificial chaos to your system. We're using Chaos Monkey from Netflix, which is a tool that somewhat randomly terminates instances running, and we even use that in production. And that is constantly exercising the fault tolerance of your system. You don't have to think, well, I think I've covered our bases, and then if a machine actually goes down, you find out you haven't. So that's a constant testing approach. Lastly, and I realize I'm surfing close to the edge here in terms of time, I wanted to look back at how search evolved. We as a team started to work on search and shipped that in Bitbucket Server last year, in Bitbucket Server 4.6. But even back then, we always knew that we wanted to ship search to both server and cloud, and we followed an approach that we called the shared component approach. Search in Bitbucket Server is essentially a set of P2 plugins that we ship with server. And you can see we have the same separation between indexing and query pipeline. So what is that shared component approach? We simply try to put as much of the common core search functionality into shared modules and libraries. And then we have different consumers that are deployment specific. So the P2 plugins that use those libraries and components in Bitbucket Server, and Java-based microservices using those components and libraries in Bitbucket Cloud. We also added a set of SPIs, stands for Service Provider Interfaces, which are essentially API definitions that are meant to be implemented by other components to extend functionality. We use that to abstract away some of the differences between those deployment environments. For example, we have a content service that defines a set of methods that allows our common shared indexing component to call out into server or cloud to retrieve content, to look up the latest commit. And then we have a Bitbucket Server specific implementation in our P2 plugin that is using the Bitbucket Server Java APIs under the cover, and an implementation in our Java-based microservices that is doing network calls to satisfy that SPI. An important ingredient, if that is something that you might think could be useful if you want to ship to both server and cloud, is that you can use Atlassian Connect. Due to the loose coupling of Atlassian Connect, that's essentially just using HTTP, you can choose whatever technology stack you want to use for your Connect plugin. And that allowed us to choose a JVM-based technology stack to implement search for Bitbucket Server, and then use that same stack for Java-based microservices in Bitbucket Cloud. Possibly the most important part of this approach is less technical, it's more, again, a bit of an attitude, is that from the beginning we were biased towards the cloud constraints. That means when we designed the permission approach, we performance tested that with numbers from cloud, even though we were only working and focusing on server. It also applies to some of the SPIs. We knew that those SPIs would be implemented by doing remote network calls. So in our SPIs, we expressed that fact that things could go wrong and might have to be retried, even though in server there's not much point or no real requirement for that. So how did it go? Were we able to build once and ship twice? Largely. So we shipped it in server, and most of those core components are still in use for Bitbucket Cloud Search. At some point, though, we allowed that common code base to diverge. And again, less of a technical problem, but there is a certain overhead if there are different teams working on the same code base with different requirements and different priorities. Whether that is an approach that is suitable to maybe an add-on or a product that you try to ship depends on your use case. Also, you cannot fully abstract away the differences. Like if you run a service that provides Connect functionality to your customers, you are running a service 24/7, which is quite different to shipping frequent updates to server customers using the marketplace. I think there's still tremendous value in building your core business functionality only once and then consuming it in different deployment-specific implementations. So looking back, we looked at our main challenges around code search-specific implementation and how we approach some of the search engine-specific problems. And we looked at some of the system architecture, so I hope that the next time you're using and trying out search in Bitbucket Cloud, you have a bit of an intuition for what happens under the covers. And we also talked a little bit about how search happened and whether that might be an approach worthwhile looking into for you. So thank you very much. I was very glad and humbled to be able to talk about that project that we've worked on for quite a while. And I hope you found it interesting and useful. Thanks.